Hi, my name is Regina Szlag, and I'm currently a fourth year chemistry student at Wayne State University, and I work in the RbCa lab. Today I'm just going to tell you about my research a little bit up to this point, and that is the synthesis and characterization of bimetallic trifluoroacetates. So bimetallic trifluoroacetates are inorganic or organic hybrid materials, meaning that they have an inorganic component and an organic component. My inorganic components are rubidium and alkaline earth metals, which are bridged by my organic component, which is my trifluoroacetate, which acts as the ligand in the system. I synthesize these materials via solvent evaporation, which in theory is simple, but it takes a lot of optimization. However, all I have to do is dissolve my metal carbonates in the trifluoroacetic acid and water, and then I heat and flow nitrogen for 2 days, and at the end I get a dry product, from which I can isolate single crystals. From there I was able to analyze the structure. So in the pink and orange material, that's my rubidium magnesium trifluoroacetate, we see tetramers, in which the pink, the rubidium, sandwich the magnesium. These tetramers are held together by the trifluoroacetates, and since there's also water in my structure, there's also hydrogen bonds contributing to the structure. The second material, the blue and pink, is my calcium and rubidium. Here, the calciums and rubidiums are connected via metal-oxygen-metal connectivity, and that extends in one dimension, making this material an extended inorganic hybrid. The same goes for the rubidium strontium, but rather than just extending in one dimension, it extends in two. After I did structural analysis, we did solid state and solution decomposition to see if we could get the mixed metal fluorides. We were able to obtain the mixed metal fluorides for the rubidium magnesium and rubidium calcium trifluoroacetates, getting the metals in the appropriate stoichiometry. And these results allowed us to conclude that both the rubidium magnesium and rubidium calcium act as single source precursors to the mixed metal fluorides. However, we were unable to obtain the mixed metal fluoride for the rubidium strontium material. Part of my characterization consisted of thermal analysis, where I was able to determine the temperature of decomposition and compare the theoretical weight loss with the experimental weight loss. The weight losses for the magnesium calcium, or rubidium magnesium and rubidium calcium materials corresponds well with the theoretical, but for the rubidium strontium there is a little bit more of a discrepancy there. In addition, for the rubidium magnesium material, I did evolved gas analysis just so we could try to get a better understanding of the decomposition mechanism to the mixed metal fluoride. And the temperature at which we saw the major weight loss, we obtained the mass peaks for carbon dioxide and carbon monoxide, which makes sense because obviously when it decomposes to the fluoride, we just obtain metals and fluorides. There's no carbon impurity or oxygen impurities present. So here are the results for the solid state decomposition. It took me a while to optimize the heating parameters to get phase pure samples, or phase pure materials, excuse me. But eventually I was able to do that, and when we decomposed the rubidium magnesium in the solid state, we got the hexagonal phase, and then we were able to obtain the rubidium calcium fluoride phase pure as well. However, when we did the solution decomposition for the rubidium magnesium, we noticed something very interesting. We got the cubic phase as a result of the solution decomposition, but when we heated the material back up, we obtained the hexagonal phase. And you can see that with the px already here. This shows the temperature going from 600 to 700. In conclusion, I was able to synthesize 3 materials, 2 of which were extended inorganic hybrids, and then 2 of which, the rubidium magnesium and rubidium calcium, acted as mixed metal fluorides. I hope you enjoyed my talk. Thank you for watching.